One of the bombs began arming itself over North Carolina, over American homes. In January 1961, a US Air Force B-52 broke apart in the sky and dropped 2 hydrogen bombs on its own country. Each bomb carried a yield more than 250 times Hiroshima. One deployed its parachute. The other did not. As it fell, 3 of its 4 safety mechanisms failed. 3. The final barrier between farmland and nuclear detonation was a single low-voltage switch. That switch held. If it hadn't, North Carolina would have been erased by an American weapon. This wasn't enemy action, it wasn't war, it was routine. And the public was never told how close it came. To understand how this became possible, you have to step back into a world where nuclear weapons were not just stockpiled, they were airborne. By the late 1950s, the United States and the Soviet Union were locked in a nuclear standoff that had no historical precedent. Both nations possessed weapons capable of destroying entire cities in a single strike. And both sides knew it. The strategy of the era was built on a brutal calculation. If one side launched first, the other had to retaliate instantly. Deterrence depended on certainty. If American bombers were destroyed on the ground, retaliation would be impossible. So military planners made a decision that felt logical at the time. If bombers were vulnerable on runways, they would stay in the air. Operation Chrome Dome began in 1960. Fully armed B-52 bombers flew continuous patrol routes, day, night, weekends, holidays, above the continental United States, across the Atlantic, along the edges of Soviet radar. At its peak, multiple bombers carrying live thermonuclear weapons were airborne at all times. Hydrogen bombs were flying above American cities every single day. The crew that took off from Seymour Johnson Air Force Base on January 23, 1961, was performing a routine rotation. 2 Mark 39 thermonuclear bombs were loaded beneath the wings, each with a yield of approximately 3.8 megatons. The flight path was normal, weather was stable, until shortly after midnight, when the crew detected a fuel leak in the right wing. At first, it seemed manageable, but the leak worsened. Fuel began pouring from the aircraft at a catastrophic rate. The crew descended, reduced speed, but slowing the aircraft increased structural stress. The right wing began to fail, metal bent, integrity collapsed. The bomber started breaking apart over eastern North Carolina. 8 men were on board, 5 would survive, 3 would not. And as the fuselage tore open, 2 thermonuclear weapons separated and began falling toward sleeping farmland below. The 2 bombs did not fall the same way. The first bomb deployed its parachute. Its descent slowed. It drifted into a field near Faro, North Carolina, damaged but stable. Investigators later determined that several safeguards had functioned correctly. It was dangerous, but it had not progressed far into its arming sequence. The second bomb was different. It did not deploy a parachute. It entered free fall from roughly 30,000 feet. As it fell, aerodynamic forces triggered internal mechanisms designed for combat release. The Mark 39 was engineered with 4 independent safety systems. 4 barriers meant to prevent accidental detonation. Redundancy was supposed to make failure nearly impossible. But the fall was violent, chaotic, uncontrolled. Switches activated, timers engaged, environmental sensors registered altitude. The bomb began moving through its arming sequence. By the time it struck the ground near a tree line outside Goldsboro, it had completed nearly every step required for detonation. Nearly. Investigators expected reassurance. Instead, they found something unsettling. The Mark 39 had 4 independent safety mechanisms. Under the conditions of that fall, 3 of them failed. A high-voltage arming mechanism activated. The timer completed its cycle. Environmental sensing switches confirmed deployment conditions, one by one. The layers were stripped away. Only one safeguard remained: a low-voltage safety switch in the firing circuit, a relatively simple electrical component. That switch remained open, and because it remained open, the firing signal was never sent. No nuclear explosion occurred. Later, analysis revealed the severity of what almost happened. 3 of the 4 safety systems had been rendered ineffective. The final barrier was a single point of failure. If that switch had closed, a 3.8 megaton thermonuclear detonation would have occurred in eastern North Carolina. The fireball would have stretched more than a mile wide. Everything within that radius vaporized. Thermal radiation igniting fires across towns, shockwaves flattening structures for miles, fallout drifting across state lines. The United States would have experienced a nuclear explosion caused by its own weapon during peacetime. And the difference between that outcome and reality was one switch. Recovery crews located the first bomb quickly. The second had buried itself deep into the waterlogged soil. Teams excavated carefully. They removed major components, but one secondary stage sank too deep to recover safely. The Air Force purchased an easement on the land to prevent future digging. Part of that thermonuclear weapon remains buried there today. Public statements minimized the danger. Officials assured safeguards had worked. Internally, reviews told a different story. Engineers re-evaluated nuclear weapons safety architecture. Goldsboro exposed a flaw in assumptions. Layered redundancy was not infallible. Complex systems fail in complex ways. Operation Chrome Dome continued for years after the incident. Armed bombers remained airborne. The program ended only after another crash in 1968 that created international outrage. On the morning of January 24, 1961, a hydrogen bomb armed itself over the United States. 3 safeguards failed. One switch held. History calls it an accident. Engineering calls it a near detonation. And the difference between those 2 versions is the difference between a quiet field in North Carolina and a crater visible from space.